Alright, so today we're going to be talking about NMR, proton NMR specifically. So NMR stands for nuclear magnetic resonance. So nuclear magnetic resonance is a physical phenomenon in which nuclei in a strong constant magnetic field are perturbed by a weak oscillating magnetic field and respond by producing an electromagnetic signal with a frequency characteristic of the magnetic field at the nucleus, hence the signals. So today we will talk about the number of signals, the position of signals, integration of signals, and spin-spin coupling. So we'll start off with ethanol here. The formula of ethanol is C2H6O, and what makes this specific NMR here difficult to understand is the alcohol peak. So alcohol right here labeled A. So the alcohols tend to be weird in NMR, and they can range anywhere from 1 to 5 ppm, which is a huge range when you're trying to figure out very specific compounds and structures. And so I have put a photo of the structure of ethanol down here. And so as you can see, the structure is CH3, CH2, and an alcohol. So the hydrogen on the alcohol will appear as a singlet, and that's because there are no splitting or spinning patterns here. And so the two hydrogens in the middle, the CH2 carbon here, are chemically equivalent because they are connected to the same carbon. And they're adjacent to the CH3 carbon here, which will have 3 hydrogens, obviously. And so because of spin-spin coupling, this CH2 carbon here will have 4 signals and will be a quartet. This CH3 right here will have 3 signals and be a triplet. And this OH right here will have 1 signal. So the 3 hydrogens on the CH3 here at the end of the chain furthest from the alcohol will couple with the equivalent hydrogens on the middle here and give off 3 signals. So that's called a triplet right here, because you can see here there's 1 tall peak and then 2 smaller peaks next to it. So 3 peaks is triplet. Now this is where the placement of the signals comes into play a little bit. So the CH3 triplet will be the closest to 0 ppm, also known as the furthest upfield. So this is upfield, that's downfield. And this is because it's the furthest from the electronegative atom, which in this case is oxygen. As you can see, just above 1 ppm here, maybe like 1.1, 1.2 ppm, there are 3 peaks next to each other, and it's a triplet. So the next peak you can see is right here, about 3.5, 3.6 ppm. And this is a quartet, so you can see the 2 tall middle peaks and then 2 shorter peaks on the outside of it. So this quartet will represent these 2 hydrogens here, labeled B, as you can see there. And it's significantly downfield compared to this hydrogens. And the reason for that is because it's attached directly to a very electronegative element, and which pulls signals downfield. So you can see the quartet just above 3.5, but right in front of it, right here, there's a 5th peak. It's a little bit more broad, it's a little shorter. And this peak equates to the hydrogen attached to the oxygen, which makes up the alcohol. So that is a very important peak, because that tells you that there's an alcohol in the molecule. So if you did not have this picture of the molecule here, you'd have to be able to see that peak and see, like, okay, it's between 1 and 5 ppm, it's more broad, and it has 4 signals right next to it, which means it's very electronegative. So then you would know that it's an alcohol. So next year we're going to be talking about ethyl acetate. So the chemical formula of ethyl acetate is C3H6O2. And I have the structure again right here for you guys to look at. As you can see, there's those methyl group right here, an ethyl group right here. And then right here in the middle, there's an ester. So we're not super worried about the ester because the oxygens in this case, they won't give us a signal of any type on this NMR because they don't have any protons. And so the signal will come from the two CH3s here on the end, and then this CH2 right here. So the structure is here to help you guys visualize a little bit where the peaks are actually coming from. And so as you can see, there's three main peaks on this structure. There's this triplet here at about 1.3 ppm. There's a singlet here at about 2.2 ppm, and the quartet here at about 4.2 ppm. So we'll start off with this singlet right here. So the singlet belongs to the CH3 right here. And this is a singlet even though there's three hydrogens because of the N+1 rule, something called the N+1 rule. So the neighbor of these hydrogens has no hydrogens bonded to it. So this carbon right here has no hydrogens bonded to it. And so that makes the value of N 0 because there's zero adjacent hydrogens. So 0 plus 1 equals 1, which is the reason there is one peak. So this peak is between the quartet and triplet here because it's closer to these electronegative oxygens in the ester than this one over here. So this is the furthest away from the oxygens. And this one is in the middle. This is the closest, so that's why the signal is in the middle. And as we know by now, the electronegative elements pull signals downfield. So the triplet shown at 1.3 ppm here belongs to the CH3 hydrogens on the end of the chain, the furthest away from the ester. So this will undergo first order coupling with this CH2 right here, these two hydrogens, and that's why it has a triplet, because these three hydrogens are coupling with these two equivalent hydrogens. And so the remaining signals here, this quartet, just above 4 ppm, that will also undergo first order coupling with this CH3 right here, and that's why it gives us 4 peaks. So this carbon here is what it belongs to. You can see the C and the C match up. And it is bonded directly to this oxygen, which is why it is pulled so far downfield. So to recap here quickly, this CH3, it's all by itself. It has no hydrogens to couple with, so it's a singlet. This one right here, this CH3 on the end, can couple with these, but it's further upfield because it's not bonded to an electronegative oxygen. And these two hydrogens right here, they can also pair with these hydrogens, but they're bonded directly to this oxygen, which is the reason that it's so far downfield compared to where it typically would be on a typical alkane. So the next proton NMR that we will be looking at belongs to 2-propanol. So 2-propanol has a chemical formula of C3H8O, and once again I have the structure here so that you guys can look at it, and it consists of a carbon right here in the middle with a methyl here, and then up here there's an alcohol attached to it. So basically a 3-carbon propane chain with an alcohol attached at the second position right here. So on the NMR of 2-propanol here, there's 3 major sets of peaks. You've got A, B, and C once again. And so there are 2 peaks, or a doublet, just above 1 ppm, a singlet at about 3 ppm, and what appears to be a quintet. It's hard to see because it's small how many peaks there are. So we can just call this a multiplet because it's more than 4 peaks. And so as you can see, based on the NMR, this first peak equates to 6 hydrogens. That's what this 6 means up here. And it's a doublet as well. And this means that there are 2 equivalent carbons somewhere in this this molecule we have here. And as you can see, these 2 carbons right here, both labeled A, they're both attached to the same carbon, which is attached to the same alcohol. So these 2 are equivalent. So this will give off one signal, this will give off one signal, and it'll make a doublet. And so this is typically where a chemical shift should occur for a typical alkane, just above 1, and that's because it's further away from the alcohol. So the next furthest downfield peak is right here, the singlet at about just above 3 ppm. And based on the structure, we're looking for a hydrogen that has no adjacent hydrogens to couple with, which would give multiple signals. And so we have, what's left is these two hydrogens here. So this hydrogen could couple with either of these. And this hydrogen is bonded to the oxygen, which has no other hydrogens on it. So it can't couple with anything. So the hydrogen attached to the oxygen in the alcohol is the only hydrogen in this atom that is not bonded to a molecule with adjacent hydrogens. And that means that this hydrogen right here will give us a singlet. And so, like I said earlier, alcohols can be between 1 and 5 ppm, and this one it's hanging out around about 3 ppm. But because it's a singlet, you can tell that it's the alcohol. It's also a little bit more broad than the other peaks. And so this leaves us with the multiplet here that lies just before 4 ppm. So this multiplet belongs to the middle carbon here in the second position with 1 hydrogen. So this hydrogen is adjacent to these 2 equivalent carbons here, with each of those have 3 hydrogens, obviously. And because of this hydrogen will undergo spin-spin coupling and should have 6 signals showing. So it's actually not a quintet, like I said earlier. So the placement of these signals are so far downfield compared to the doublet here just above 1 ppm because, as we know, it's attached to an electronegative oxygen, and that pulls the signal further downfield. So now we'll look at a little bit more complex molecule here called aspirin. It's the final NMR that we're going to look at in this video. So I hope you guys are starting to understand it a little bit better now. So the IUPAC name of aspirin is actually 2-acetoxybenzoic acid, and the chemical formula of aspirin is C9H8O. So this proton NMR has significantly more peaks than the 3 that we just described. But what's really important about interpreting this type of data is to not freak out when you see something like this. Use the same techniques and the same deduction that you just already have previously learned. You just have to do it with a few more peaks. So don't freak out. Just take your time and work through it slowly. You will figure it out. So once again, I have the structure here for you guys below, and we have A, B, C up here. And it's easier to visualize what I'm talking about, I think, if you guys can see it. Even though on any exams and stuff, you might not have the structure. But this NMR has 5 major peaks, or sets of peaks, I guess, anyways. So the first one here is a singlet at about 2.2 ppm. And then there's 3 sets of multiplets here between 7.8 and 8.2 ppm. And the first thing that I want you guys to notice when you looked at a spectrum like this is the singlet right here, that little peak there at 11 ppm. So this peak is small, but it's a very important peak, and if you miss it, it'll make your life a lot more difficult when you're trying to determine a structure. So this peak, as you can see, is slightly more broad than the rest of these, and although it's short, a slightly broad peak at about 11 ppm indicates a carboxylic acid hydrogen. So in the grand scheme of things, aspirin is not a complex molecule, and noticing this little small peak that indicates a carboxylic acid basically covers 1 out of 3 of the major parts of this molecule. And so as you can see here, the other groups are this aromatic here labeled C, and then the ester right here that's labeled B. So now we're going to talk about the furthest upfield and the tallest peak on this spectrum, which is the singlet at about 2.2 ppm. So this singlet, this peak is a singlet because there's no hydrogens bonded to the adjacent atom, which is right here. There's no hydrogens attached to this carbon, so there's nothing for it to pair with, and it's bonded to an ester. It's part of an ester, so that's why it's a little bit more upfield, because a typical alkane would be less than 2. It would be more closer to 1 ppm, but due to the placement of this hydrogens, the signal is slightly further downfield. So now looking at the remaining 3 peaks around 8 ppm here, it's blown up here, so it's a little bit easier to see. It's hard to tell from the specific from this NMR, I guess, exactly the number of peaks that each group has, but in this area, when there's peaks like this, knowing the exact number isn't totally relevant. And that's because, from what we've learned, aromatic hydrogens can range from about 6.5 to 8.5 ppm, and there's not a lot of other groups that can lay in the 6.5 to 8.5 region other than amides. And based on the molecular formula we're given and the drawing of the structure right here, we know that there's not an amide. There's not an amide in this structure. So we can come to some conclusions about connectivity as well. And since we have a peak for a carboxylic acid and a peak for a CH3 attached to an ester, we know that this leaves 4 sites on the aromatic open for bonding. And since there are only 3 peaks or 3 signals, we can conclude that 2 of these hydrogens, so that'll be these 2 hydrogens right here, they're equivalent. So that they're only going to give off 1 signal each. So the furthest downfield peak in the aromatic region, right here, this one, also this one, corresponds to the most deshielded proton, which is the hydrogen closest to where the ester is attached. And the lowest peak corresponds to the hydrogen closest to where the carboxylic acid is attached, so that's here. And each of these multiplets have multiple peaks because of the spin-spin coupling that occurs between the hydrogens. So these ones compare with this one compare with this one's pairing with this one, so there's lots of pairing going around. So that's why there's all these little peaks in here, and you can't tell exactly how many there are. But that's, not totally irrelevant, as we said earlier. So down here we have singlet for the CH3 N+1 rule. It's not attached to any other hydrogens, therefore it's 1 peak. We have here C, the aromatic, at around 8 ppm. That gives off multiple very close signals. And then we have A, this important little peak here that it's easy to miss if you're just looking at the spectrum quick, but that's very important because it covers this whole carboxylic acid. So that basically concludes this video, and I hope you guys were able to learn something about proton NMR, and thanks for watching.